Today we're going to be talking about, or at least starting to talk about, the Monge-Ampere equation. So this is the part of the class where I get excited, I guess, a little bit, because the Monge-Ampere equation has been one of my big areas of research, especially the numerical solution. This is the PDE, Monge-Ampere. Okay, so the PDE, which we've written down a couple times already this semester, is that g of the gradient of phi of x times the determinant of the Hessian of phi is equal to f of x. And our expectation is that the solution we're looking for, phi, should be a convex function. Right, and we expect that if we can solve this PDE, then the gradient of phi is going to give us our optimal transport map, at least formally, if things are smooth enough. And we know that even when things aren't completely smooth, we kind of almost everywhere expect the solution of our transport problem to be the gradient of a convex function. OK, so this is nice. This brings optimal transport into the realm of PDE theory. So we can use a lot of our PDE tools to study this, to solve it. So let's make a few observations. Is this a well-posed equation? So say I give you this PDE in a bounded domain. So in some domain, omega. Are we good to go? Can I sit down and write down a unique solution of this? No, why not? What kind of conditions? I don't have boundary conditions. So one thing we expect from a PDE like this is that we need some kind of boundary condition. Actually, you could look at this and say right away, this is clearly, if there's a solution, it's clearly not unique, because if phi is a solution, then phi plus any constant is also a solution. So we clearly don't have uniqueness. But we expect that we're going to need some kind of boundary conditions. I'm going to start simple, and for now we'll just work with the Dirichlet boundary condition. Then later on we'll talk about what boundary condition really makes the most sense in the context of optimal transport. But for now, let's just use homogeneous Dirichlet conditions. Okay, so that means we're going to set not u, but phi equals 0 on the boundary. Okay, so that's somewhere to start. So now I have a PDE. I have a boundary condition. Now, we know from the work we did on optimal transport that at the end of the day, we expect the solution to be convex. I've actually written it here as a condition, but do I need that there? Could I just cross this off and say, let's solve the PDE like this? Some nodding. So what you expect from the PDEs you've seen, maybe Poisson's equation or whatever, is that you have a PDE, you have boundary conditions, you're good to go. That's great for linear problems. This is extremely nonlinear, and in fact, that's not good enough. You can just think about the simplest linear equation that you want. Let's solve y equals mx, whatever, and for any value of there's going to be one x-intercept or one y-intercept. But as soon as you have a quadratic equation, right, you get multiple solutions of a quadratic equation. This is not linear and is susceptible to this problem of having multiple solutions. So in fact, let's remove the convexity constraint for a minute. And let's suppose that phi is any solution, okay, of the PDE and satisfies the boundary conditions. Okay, well then right away I can say, let's do a simple case of the P and boundary conditions. Let's do a simple case where the right-hand side is just equal to 1 and phi is equal to 0 on the boundary. Okay, so I found a solution of this. Right away I can write down a second solution. So assuming, let me put one more condition, we're in R2. Right away I can write down a second solution. If phi is a solution, minus phi is a solution. Okay, and then minus phi is also a solution. Right, in 2D, okay, the Hessian is this 2 by 2 matrix. When you take its determinant, you're going to have this sort of quadratic structure, right? So your minus sign is going to cancel itself out when you start squaring things or taking products. Okay, minus phi doesn't affect the boundary conditions at all. So we don't have uniqueness without the convexity constraint. Uniqueness without the convexity condition. Okay, so when I write this here, it's not a case of here, solve the PDE. Once you've solved it, you get a solution and you just check it, and lo and behold, it happens to be convex. You actually need to enforce this condition along the way. Otherwise, you may have 2 solutions, or you may have more solutions. You don't know, but certainly you don't have uniqueness. So this is something special about this PDE. It's actually a constrained PDE, and the constraint is important. And that makes things interesting when you go to try to solve this thing numerically, because now you're not just sort of solving a PDE plus boundary conditions. You have this extra constraint that you have to build in somehow. Okay, let's ask a little bit more about what the solutions look like. So how do solutions behave? Okay, so let's look at this example again. 2 dimensions, and I'll just let my boundary be a square because a square is easy to work with. Okay, so let's consider a solution of, okay, the determinant of the Hessian in 2D, I'm going to write out what it is. So phi xx, phi yy, minus phi xy squared is equal to 1 in, say, a square. Okay, and phi equals 0 on the boundary of this square, and phi is convex. Okay, let me write the domain. Let me draw the domain. Now I want to see a little bit more about how the solution behaves. So I'm going to start at a point, say, on the left side of this square. So maybe I decide to focus in right here. So let's consider a point. Say 0, y on the left side of the domain. Okay, we have a boundary condition. U is equal to 0 all the way along here, right? So we can say something about the derivatives of phi here, right? In the y direction, the derivatives are all 0. The second derivatives are 0 because phi is constant along here. So certainly, phi yy equals 0 at this point. Okay? And this is because of the boundary condition. So we can learn a little more about phi by saying, okay, phi yy equals 0. Moreover, we have a PDE that phi satisfies, that involves phi yy. We can plug that in here. So from the PDE, what do we get? We get that phi xy squared plus 1 is equal to phi xx, phi yy, which is 0. Okay, so what does that tell us about phi? What functions phi make this true? You're having trouble coming up with one, I hope, right? This is a problem, right? Here we've got something, if phi is a real value, which we're expecting it to be, right? Here we've got something bigger than 1, and here we've got something that's equal to 0, and this doesn't work. So what was the problem? I started by assuming that I could take whatever derivatives of phi I wanted to. In other words, I assumed that this has a nice classical C2 solution, and derived a contradiction from that. So this is another issue. This is a simple example, right? I've picked my right-hand side equal to 1, which is about the simplest you could hope for. I've picked, it's just a constant. I've picked my boundary condition to be homogeneous Dirichlet, which is the simplest thing you could hope for. I've picked an extremely simple domain here, the square, which is about the easiest thing you could hope for. I could have rounded out the corners of the square and made this a perfectly smooth domain, and the same argument would have still gone through. So it's not the corners of the domain that are causing problems. And even in this very simple case, we cannot write down a smooth solution. So here the problem was we must not actually be able to take all these derivatives. Okay, so if we're going to solve this PDE, even in the very simplest cases where we're sort of using the simplest artificial boundary conditions we could think of, we need some concept of a weak solution, some way to make sense of what does a solution of this PDE look like. But certainly it doesn't have second derivatives that exist all the way up to the boundary in a nice way. Okay, so we need some sort of concept of weak solution. Our expectation is we'll get a solution that satisfies this equation almost everywhere, but there are going to be some points where it doesn't work. Right? We're looking for something convex, so the convex thing is going to have derivatives almost everywhere. But somehow we've got to do the right thing at points where we're not smooth. What are some techniques that you've seen for writing down weak solutions of equations before, of PDEs? Testing it with a regular function, and how do you move the derivatives onto the smooth function usually? Integration by parts, yeah. Okay, that was the suggestion that I was looking for. So what you will have often seen done with elliptic equations is you say, all right, I'm going to take my equation, I'm going to multiply it by a smooth test function, and then I do integration and I do integration by parts to move the derivatives off of here onto my smooth test function. And now I have an expression that doesn't require me to take all these derivatives that may not exist. That doesn't work here. So that would be great if you had an operator that was sitting here in divergent structure. So if I had something like the divergence of a grad u, then, OK, integration by parts lets me move this divergence right over. Here I have something that is fully nonlinear, right? Integration by parts with something like this is not going to be easy, and it's not going to be very helpful. You actually can write this in a divergent structure, but what's inside your divergence actually still involves second derivatives. So even when you start playing with integration by parts, you still need to take second derivatives of this thing. OK, so it's a good suggestion. It was the suggestion I was looking for, and it won't work here. So using integration by parts, OK, to transfer derivatives onto smooth functions. OK, doesn't work for a non-divergent structure operator like this. That's one of the reasons why numerical solution of this equation is challenging and hasn't been done so much until recently, because a lot of the standard tools that you'd use, Galerkin and projection type methods, your finite element methods, kind of rely on using integration by parts to move things around, and you can't do that here, which means really if you want to solve this in kind of a really careful way and have some rigorous analysis, you may need some new methods. OK, so let's think about how we can kind of try to come up with a notion of how we interpret this even when we can't take derivatives. What kind of PDE do you think this is? You've got your kind of three basic categories. Does this feel more like Laplace's equation, the heat equation, or the wave equation? You think Laplace? Anybody want to disagree? Nobody's brave enough to disagree. OK, no, you're right. So this is an elliptic equation. So let's think a little bit about what makes this elliptic. What are the important properties of elliptic equations, and how can we try to feed those properties into an interpretation that doesn't require us to take derivatives? OK, so first of all, I'm just going to note that this is a matrix, yes, the Hessian. It's a symmetric matrix. If phi is convex, what can I say about this matrix? It's positive semi-definite, yeah. So for phi convex, which is what we're hoping for, d squared phi I'm going to write is, okay, by this I mean positive semi-definite. I think I've probably used that notation before. OK, so that's good. There's a couple other things we could note. We could rewrite the determinant, our PDE operator, as okay, the determinant is the same as the product of the eigenvalues, yes? Okay, so we could write this as the product of the eigenvalues of phi, of d squared phi. Okay, and if phi satisfies the constraint, okay, so phi is convex, the Hessian is positive semi-definite, so we know about these eigenvalues what? They're non-negative. Okay? Okay, so we can say that all of these eigenvalues are greater than or equal to 0 if phi is convex. Okay, so let me write my PDE like this. I'm going to write it in kind of an operator notation. So very abstractly, it depends on x, it depends on the gradient of phi at x, it depends on the Hessian of phi at x. Okay, subject to the Hessian being positive definite, and boundary conditions. You can think of the boundary conditions being absorbed into here too. Okay, and this is the form of the operator. So f for given inputs, so x is some value in the domain. Okay, gradient of phi, which I think I call it z usually. Maybe I'll call it p. Okay, so p is some value in Rn. M is some symmetric positive definite matrix. Okay, and I can write this as, okay, minus g of p, as g of the gradient, times the determinant of this matrix, in other words, the product of the eigenvalues of this matrix, plus f of x. And we want this to equal 0. And our constraints were all of these eigenvalues were non-negative. So if I'm going to classify a PDE as, elliptic, parabolic, hyperbolic, what typically matters is how does the PDE depend on the highest order derivatives. So what really matters is how we depend on m, or maybe how we depend on the eigenvalues of m here. So if we look at it a little bit, okay, we're multiplying things together, but we're multiplying things together that are restricted to being positive. So that means if I increase any one of these lambdas, right, so I have a bunch of things I'm multiplying together, I increase one of them. Since everything was positive, the value of the product goes up, right? That only works because everything was required to be positive. That means the value of the operator goes down. So in other words, this operator is a monotone decreasing function of the eigenvalues. So f is a monotone, we'll say non-increasing function of the eigenvalues. If we restrict our attention to our constraint set, and only if we restrict our attention to the constraint set. So this is important, if we restrict to the constraint set. What other PDEs do you know that have a kind of monotone dependence on the eigenvalues of your Hessian matrix? We've said the name of this PDE already today, right? It's, Laplace's equation. Okay, you're not used to seeing it written in terms of the eigenvalues of the Hessian. But we can do that. So we can say this is also true of the Laplacian. Okay, so if I write minus the Laplacian of u, say, right, the Laplacian is the trace of the Hessian. The trace is nothing but the sum of the eigenvalues. This time we don't need a constraint to make it true because we're adding things together, right? So this is true no matter what u is. Here, you can kind of see from it here even why we need this extra constraint that we didn't need for Laplace's equation. We need it to get this sort of monotone behavior. So this is how I'm going to define an elliptic operator based on this kind of monotone dependence on the eigenvalues of the Hessian matrix. Okay, so f of x, grad u of x, and let's write it as a function of the eigenvalues of our Hessian matrix. Is an elliptic operator or a degenerate elliptic operator. Okay, degenerate elliptic operator if it is a non-increasing function of these eigenvalues. Okay, so using this definition, okay, the Laplacian is an elliptic operator, which is good. We better be able to capture that in our definition. So certainly the Laplacian is elliptic. Monge-Ampere is elliptic, but again, not for all functions. It's only going to be elliptic on the space of convex functions. So Monge-Ampere is elliptic on the space of convex functions. And where the minus sign goes depends on which author you read. So don't be confused if you read Evans and he writes this, and then you read Tsuganidis and he writes this, and they both mean elliptic. So just a note when you're reading papers on this is try to make sure you know which way the author is making the signs go, because it will matter to how the rest of the analysis goes. Okay, so we at least have sort of categorized this PDE as an elliptic PDE, and we have some idea maybe what elliptic should mean. Now, we still, our goal is to come up with the notion of weak solution that says how do we identify a solution of this equation without taking derivatives. So we've said somehow this belongs to the same family as the Laplacian. So let's just think a little bit about what we know about the Laplacian. What are some of the key properties that maybe we'll go through for us here? So let's think about properties of the Laplacian. That maybe, hopefully, will generalize. One thing we know about harmonic functions, right, is we've got a maximum principal. So we can write that one down as a candidate for something useful. Okay, so I'm going to write if U is, say, subharmonic, by which I mean negative Laplacian is less than or equal to 0. And again, the direction of this depends on who you're reading. Okay, then any maximum is going to be attained on the boundary. So the maximum on a closed set of U of x is going to be equal to the maximum on the boundary. Right, and superharmonic functions will satisfy a minimum principle. You've got a maximum principle. You have a comparison principle, which is really your uniqueness result. Okay, so this says if we have two functions, if minus Laplacian of u is less than or equal to minus Laplacian of v on a domain, so the operators are ordered on the domain, and then you get to the boundary, and the function values are ordered on the boundary. So, and u is less than or equal to v on the boundary. Right, then u is less than or equal to v everywhere. Okay, so we have maximum principle, we have a comparison principle, we have uniqueness, which is actually a direct consequence of the comparison principle. Sometimes the comparison principle is actually referred to as your uniqueness principle or uniqueness result. We have some relationship between the value of the Laplacian and local extrema of a function. Right. Obviously, we know for something that's subharmonic, the extrema the maxima happen on the boundary. But let's think a little bit more about how local max or mins behave. Okay, so let's say u is smooth enough that I can take the derivatives. And I'm not assuming it's harmonic at this point. But let's suppose that it has a min. Okay, at some point x naught. Okay, our first derivative test, I'm just doing basic calculus at this point. Our first derivative test tells us that the gradient should vanish here. Okay, our second derivative test tells us that the Hessian, right, is positive semi-definite at this point. And that should tell us something about how the Laplacian behaves, because the Laplacian, right, is directly a function of this Hessian matrix, and in particular of the eigenvalues of the Hessian matrix. So I've just written down here that at this point x naught, all of my eigenvalues are greater than or equal to 0. That's what I've written here, right? If the eigenvalues are all greater than or equal to 0, then this Laplacian has a definite sign. Right? So this means that minus the Laplacian of u of x naught, right, which we said is the sum of these eigenvalues, is definitely less than or equal to 0. So these are some key properties that you study when you study the Laplacian. Now our hope is that in some way these generalize to other operators that are elliptic, and in particular that I can kind of use these concepts to build a definition of a weak solution. So I'm going to start with a Poisson's equation. I'm going to see if I can use what I know to be true about the Laplacian to come up with a way of taking a function. Let's just start with a smooth function that is a solution of Poisson's equation. And I want to test that whether it's a solution of Poisson's equation. And I want to test it in a way that doesn't require me to take derivatives. Okay, so let's start by assuming we have something that's smooth enough. Okay, let's suppose that minus the Laplacian, say of x plus f of x is greater than or equal to 0. Okay, in other words, U is a supersolution of this Poisson equation. Now I'm going to just focus on any point x naught in the domain, and we're going to see how we can kind of test this or use this fact. So let's pick any x naught in our domain and see what we can learn about this. Okay, so here's my u, whatever it is. Here's my x naught. I have some tests here that kind of say how my operators should behave at different points. Now, I can't sit here and assume that I'm sitting at a minimum of u, because I need to test this equation everywhere. So let's bring in another function. Ideally, a function that we're going to move derivatives onto, because just like with integration of my parts, you bring in a test function that's smooth and you move the derivatives onto it. I want to bring in a test function that's smooth here that I can move derivatives onto. But I can't do it by integration by parts. I need some other argument. So let's bring in a test function that's smooth. I'll call v. And let it touch u at one point. So this is my u. This is my v. So we introduce a smooth test function. All right, we want to, v is smooth. We want to take derivatives of v. We don't want to take derivatives of u. Let's use what we know about local extrema. So I've set this up so that u minus v has a local extrema at this point x naught. Okay, so let's suppose u minus v has a local, let's see. U is bigger than v, and it's 0 here, so it has a local min here. Has a local min at x naught. Okay, so I've just picked any v such that this is the case, right? There's lots of ways I could put smooth functions here that have this property. Any way of hitting this from below by a smooth function will work. And I say, OK, we've got a local min. I have some conditions of what should happen at a local min. And these conditions happen to involve the Laplacian. And I really want to involve the Laplacian because that's what's coming up in my PDE. OK, so I know that minus the Laplacian of u minus v at this point should be less than or equal to 0. tend to give you the definition as Sukanides would define it, because I think it's a little easier to work with. All right, this is right. So this is my candidate for a test. So I'm going to write down the test for Poisson's equation, and we're going to see if it works. So here's an example. Okay, let's suppose U is smooth. And let x not be any point in omega. And let's suppose that whenever v is a smooth function, such that u minus v has a local min, we said. Okay, then left-hand side, right-hand side, and we throw out the middle. So we're not taking derivatives of u. Okay, so then minus Laplacian of v plus f is greater than or equal to 0. Okay, so I'm holding a function, which for now I'm assuming is smooth, just so we can test and see if things work. If this doesn't work for smooth functions, then it's not going to help us out for more challenging problems. But I have a test that doesn't require me to take derivatives of u. Now I want to check and see if this test is equivalent to saying that actually u is a supersolution of Poisson's equation, just in the usual sense. So this is my question. Does this imply that? Is this enough to be equivalent to imply that u also satisfies this inequality? Okay, a lot of these arguments are going to involve building clever test functions, right? So this test works for lots and lots of different test functions. I need to find the right test functions to put in the definition to somehow cause this inequality that I want to fall out. So what I want to do is pick functions v. Okay, I need to make sure they lie below u, but I want to try to get them kind of up snug and tight with u locally, so that somehow the second derivatives of v are very close to the second derivatives of u. Okay, so let's try this. Let's consider v to be equal to, and I'm going to try a simple quadratic function. But I'm going to try to get a quadratic function that hugs this as closely as possible. There's no mystery about how to do that. This is nothing but a Taylor expansion, Taylor approximation. Okay, so let's do a second order Taylor approximation with a little twist. Okay, plus a gradient of u dotted with x minus x naught plus 1/2 x minus x naught transpose d squared u of x naught. Let's leave a little space here. X minus x naught. Okay, so far I've got just a second order Taylor approximation, which if u is smooth enough, you know, these lie close together. It's not quite good enough for these to lie close together. If I'm going to use the test, right, I need u minus v to have a local min here, which in other words, in a neighborhood of x naught, I need v to be sitting below u, right? So this is close to u, but it could be above or below. We don't know. I need to tug it down a little bit. So I'm going to tug it down a little bit. Okay, I suggest this as a test function. All right, again, this is, most of this is just a second order Taylor approximation. So this is u of x plus something that's smaller than x minus x naught squared. And then I have this extra term, minus epsilon over 2 times x minus x naught squared. Okay, so what do I have? V is equal to u minus something positive plus correction terms that are even smaller, right? So this is certainly less than or equal to u as long as we're close enough to x naught. So this is true in neighborhood of x naught. Okay, so I've built a test function that satisfies this condition. U minus v has a local minimum at this point x naught, right? V touches u here, right? It touches u here. Here, if I put in x naught, these go away, and I'm just left with u of x naught, and it's sitting below it everywhere else in the neighborhood. Okay, so this is a valid test function. So we said straight away we know. Okay, from our test, we have that minus the Laplacian of v plus f of x naught is greater than or equal to 0. And we can certainly compute the Laplacian of v. Right? It's a constant term. This is our linear term. It doesn't matter. Okay, the Laplacian is going to be the sums of the eigenvalues of these guys. We can break it up. We've got the Laplacian of this minus epsilon times, the trace of the identity matrix. So what am I going to have? I'm going to have minus the Laplacian of u, okay, plus epsilon times the trace of the identity, that's n, plus f of x naught is greater than or equal to 0. Right, and this works for every epsilon greater than 0. So taking epsilon to 0, we get that u is in fact a supersolution of this Poisson equation. So what did I do? I wrote down a test here. And it's a test that doesn't require taking any derivatives of u at all. But somehow, just satisfying this test that doesn't involve derivatives of u is enough to guarantee that we do have a supersolution of the right equation. Right? So this is a test that does the right thing with smooth functions and for our Laplacian. But it's a test, again, that doesn't require derivatives of u. So I could try this test on other functions that don't have derivatives. Okay, so in other words, this test for u being a supersolution of Poisson's equation, it works. First of all, we just checked that it works. Doesn't require taking derivatives. Somehow we've used not integration by parts, but some of these kind of maximum principal type properties to transfer derivatives off u onto a smooth test function. All right, that's a lot of work for Poisson's equation, but the hope is that we can do this not just for the Laplacian sitting here, But maybe for other elliptic operators where, I can't do integration by parts, where we know that we're going to have problems with regularity, right? We know that we can't just expect to look for smooth solutions. So this motivates the definition of the viscosity solution. Okay, so I'm going to write down exactly the test that I wrote here, but instead of having a Poisson equation here, I'm going to put some other elliptic PDE. And we're going to say that U is a viscosity supersolution of the elliptic PDE, f of x, grad u of x, d squared u of x equals 0. If, for every smooth function phi, such that u minus phi has a local min at some x naught, then automatically, if we plug phi into this operator, we get the correct sign. Right, it's exactly this test, which we know works for the Poisson's equation. We knew really that the key to this working was the fact that this depended in a monotone way on the eigenvalues of our Hessian matrix. So it's reasonable to say, let's put a different elliptic operator here that also has this monotone dependence on the eigenvalues of the Hessian matrix. And hopefully this still gives a reasonable test. So this is for supersolution. We do the same thing for subsolution. We just switch everything around. So we say that U is viscosity subsolution of the equation if, and we just switch everything around. Okay? So if U minus phi has a local max at x naught, then the PDE operator applied to our smooth test function is negative. Right? That just amounts to putting test functions above here. And if you give me a function and I test it and it looks like it's a subsolution, and you test it again and it looks like it's a supersolution, then I say, great, maybe I'm actually holding a solution to the PDE. So we're going to say that U is a viscosity solution if it is both a sub and a supersolution. Any questions on the definition or the work leading up to the definition so far? Why is it called viscosity solution? That's a great question. The name viscosity solution is dumb. That's the short answer. But I can give you an idea where it came from. It came from the concept of vanishing viscosity solutions. So when I wrote down the definition of elliptic operator, I said we've got something that's somehow a non-increasing function of the eigenvalues of the Hessian matrix. So a simple example of a PDE that satisfies that condition is something like this. This is, in fact, a non-increasing function of the eigenvalues of the Hessian matrix. You're not used to thinking of this as an elliptic operator, but that's where I wrote down actually the definition as degenerate elliptic. This is degenerate to the point where the second derivatives fell out of the equation. Actually, the theory all works for this. So the theory of viscosity solutions, these kind of maximum principal arguments, comparison principal arguments also work for this equation. Actually, they're usually a lot easier for this equation. Okay, this is kind of a hyperbolic operator, but you can think of it as elliptic or degenerate elliptic. Now, what's one of the approaches that's been used to find weak solutions of this thing? This is the iconal equation. So let's do a simple example of it. U prime minus 1 is equal to 0, say in minus 1, 1, and u at plus or minus 1 is equal to 0. Okay, so we're 0 here, and we should have slope 1 in between. So there's no way to write down a smooth solution of this, right? If this goes up with slope 1, at some point it's got to turn around and come back down with slope 1. And you can't do that in a smooth way. There's going to be a corner, and there's lots of ways to write things that have corners. So I could do this, I could do this, I could just go zigzag, zigzag, zigzag. And you need a concept of a weak solution. So one of the first things that people did was say, let's try to smooth this out a bit. Let's use vanishing viscosity. Let's take this first order equation and use a second order regularization term. And let's instead solve this. So we add this little viscosity term, epsilon times the Laplacian in higher dimensions. And now this is going to try to smooth things out. Okay, so let's see, what's this going to do? If you have something like this, then u prime is less than 1, negative here. So it wants the second derivative to also be negative. So it's going to give you this solution. By the way, this is an example of a problem where this is the solution of u prime minus 1 equals 0. And this is the solution of 1 minus u prime equals 0. So multiplying both sides by minus 1 actually changes the equation and changes the solutions, which is not something that you see every day. But here it actually matters. So adding this small viscosity term was kind of an obvious, simple thing to do. And then more work was done with these. It was found an alternative that's equivalent for this problem is you can use this definition of viscosity solution and make these maximum principal arguments. So this was vanishing viscosity, and then it morphed into, well, maybe we can do other perturbations, do these maximum principal kind of arguments. It's sort of equivalent, and those got called viscosity solutions. And then they got extended to second order equations. This was no longer particularly relevant, but the name stuck, and it's a dumb name now, but we're stuck with it for historical reasons. If you're trying to get your head around some of the viscosity theory, it's easier to do starting with these first order equations, though. So again, many of the ideas are the same, but a lot of the work is easier here. And actually on Canvas, I posted a link to a book by Koika, a beginner's guide to viscosity solutions, something like that. So he'll talk about, I think, first and second order equations, but some of the work there, motivating it in a very simple way, if you're interested. Any other questions on this definition? That was a long answer to a short question, but yeah.
Is this for only elliptic F or
This is for only for elliptic f. I mean, you could write down this test for anything you want, but it might not be meaningful or give you any kind of way of having solutions exist or be unique. So elliptic f, but degenerate elliptic f. So in particular, if you had something like the heat equation, which is parabolic, again, you can think of this as degenerate elliptic, that the second derivatives in t fell out of the equation, but this would still work. And actually going through and proving that this gives you a well-posed definition even for elliptic problems is very problem-specific. For first-order equations, it's kind of easy to make general theorems about uniqueness, for example. For second-order equations, the results are often very highly problem-specific. And sometimes you need to tweak things a little bit, or even tweak what you mean by uniqueness. All right, so this, in this definition, I said let's look at all phi that are smooth. Now, here, this was for an operator that was, as you pointed out, is for an elliptic operator. Monge-Ampere is elliptic, but only on the space of convex functions, right? So when we write down this definition for Monge-Ampere, we should actually change it a little bit and say, let's not look at all smooth test functions. Let's look at all smooth functions that are also convex, that actually live within the correct space that we're interested in. So these are just some remarks. For Monge-Ampere, we should only use phi belonging to C2 that are convex. In other words, that live in the space where f is elliptic. Otherwise, these kinds of maximum principal type arguments don't make sense anymore. You still need the constraint. So this test isn't going to guarantee you that your U is convex at the end of the day. What you can do is to say, here I found a function that's convex. Now let me put it through this test, and I can check and see if it satisfies Monge-Ampere. So we still need the convexity constraint. Although I think in your next homework assignment, I put a problem where you get to see how you can actually take this constrained PDE and rewrite it as an equivalent unconstrained PDE, and build the convexity constraint right into the PDE. So you get to play with that in the next couple weeks. What else? So we know we don't have to take derivatives, but what kind of regularity do we expect in our solutions here when we're working with viscosity solutions? Well, we're doing something where we need to be able to make sense of local mins and local maxes at the very least, right? So when testing, if U is a super solution, I need to make sense of local mins of U minus phi. Okay, phi is smooth, so we don't really care what's going on there. He doesn't affect things. The real question is, what do I need to be able to make sense of local mins of U? I don't need it to be smooth. I don't need it to be continuous even. But something like this, for example, something like that's not so good, right? So if I have a jump like this, I don't have a local minimum. So this is not so good. But if I move things around a little bit, in this picture I do have a local minimum. This is okay. So what's the level of sort of regularity that gives me this picture, that makes this okay? So I don't necessarily have a subgradient here. It's lower semi-continuous, exactly. So this is lower semi-continuous. Okay, so we want super solutions to be lower semi-continuous. Okay, what I mean by this is that f at a point is less than or equal to the limit inferior as we approach that point. All right, so in this case, the limit inferior going to this point is this value here, but f is way up here. That's no good. In this case, the limit inferior is down here, which is equal to f. That's fine. I could have put a whole ear in here and put the value of f way down here, and I'd still have a minimum, and that would still be fine. So we want super solutions to be lower semi-continuous. Then on the flip side, if I'm looking for subsolutions, then I have the opposite picture where I want to find maxes, local maxes. So we want subsolutions to be upper semi-continuous. Okay, and that's the opposite thing here. Okay, then at the end of the day, I find something and I go through the test and I say, oh, it's a subsolution and it's a super solution, then it's my viscosity solution. So if it's both upper and lower semi-continuous, then it's actually continuous. So we expect viscosity solutions to be continuous. You can relax that for some equations and have discontinuous viscosity solutions where effectively you just look at the upper and lower semi-continuous envelopes. Sometimes you need to do that, but for most of what we care about, this is good enough. Continuity is good enough. In particular, we're looking for a convex function, so we know it's going to be locally Lipschitz inside our domain. But it turns out using this lower regularity, you actually really need, once you start thinking about building numerical methods and doing the convergence proofs, you can't assume that these things are continuous. Okay, so we expect continuous solutions, and for Monge-Ampere, we expect convex, and thus locally Lipschitz solutions. What other notes? Comparison principle. The comparison principle is important. So we wrote down that we know Laplacian has a comparison principle. We like it when we're working with elliptic operators that also have a comparison principle. So we're going to say that the operator, the elliptic equation, has a comparison principle if whenever, now I don't want to take derivatives of u and v, so I'm going to say whenever u is a subsolution and V is a super solution. And they're ordered on the boundary. Then they're ordered everywhere. Okay, this is the same, basically the same thing we had for the Laplacian. I've just got now a more sophisticated test for you being a sub or a super solution. And not all elliptic PDEs actually do have a comparison principle. It makes life so much easier when you do have one. It is generally a great headache trying to prove that you do have one, though. What else? Comparison right away implies uniqueness. Right? If you have two viscosity solutions, U and V, then you can say, well, if they're both viscosity solutions, then in particular U is a subsolution, V is a super solution. They're equal on the boundary, so U is less than or equal to V. And then you can reverse the argument and say, well, they're both viscosity solutions, so actually V is also a subsolution, and U is also a super solution, so V is less than or equal to U, and the uniqueness falls right out. You don't always have comparison principles, though, so this is when life is good, and then it's a lot easier to do numerical approximation. Another remark, you can interpret your boundary conditions in a classical sense. So sometimes we really want to interpret our boundary conditions in the usual classical sense. Right? So in other words, you've given me Dirichlet data, say homogeneous Dirichlet data. That means that my solution U should be equal to 0 on the boundary. Sometimes, we've talked about how sometimes you can't interpret the PDE in a classical sense. Sometimes you can't interpret the boundary condition in a classical sense. There just isn't a smooth solution that satisfies it. And this actually ends up being the problem for the Dirichlet condition in some cases. Sometimes we need to also interpret boundary conditions in the viscosity sense. Okay, so in other words, you might have an operator something like this, where you say, okay, well, in the interior of my domain, maybe it's equal to Monge-Ampere. And at the boundary, it's equal to, say, I'm looking for homogeneous Dirichlet conditions. Something like that. And then you say, now I can apply my viscosity test here, but I could also apply my viscosity test to the operator at boundary points. And now the operator has some definition at boundary points. And sometimes you need to do that. We're not going to worry about that too much, I think, in this class, but it is an issue. Any other questions on that? So I think next class, I'm going to do kind of a concrete example of this. Let me give you a solution of Monge-Ampere equation that doesn't have second derivatives everywhere, and let's see if it's a viscosity solution, see how we make this definition actually work in practice. So we're going to do that. And then I'm going to move on to a second possible way of identifying weak solutions of the Monge-Ampere equation that's actually a little more general than this. But I will leave you there today.